component to them. So you have to check very well that your initial value problem is formulated in a way that it actually can be solved in the first place, okay? So it's like a solvability condition, okay? And the idea with method of characteristics is that we want to come up with some method for which we can solve first order quasi-linear PDE, okay, where the nonlinearities are just going to be in the low order terms like U, okay? And the idea, and this is a trick we'll come back to over and over again in solving PDEs, is to reduce it to a system of ODEs, okay, along some special curves, okay? And what are these special curves called? These are the curves called the characteristics, okay? And in the case of the transport equation, we saw that the characteristics were just these straight lines, okay? Along those, basically what was happening is that our initial condition just got translated, okay? But what would happen if those lines were curved? What would happen if those lines sort of compressed in different ways? Then you would get this reshaping of your initial condition in a way that you don't see in just sort of linear transport, okay? And that's the kinds of things you can track with more nonlinear characteristics by method of characteristics. So just to get our feet wet a little bit with this, okay, before kind of going over the wholesale theory of method of characteristics, let's talk about a more general transport equation, okay? So this is a formulation of the transport equation where the speed out in front, it may not be constant. It may be some function of u, like it is in Berger's equation, okay? Still, we're going to have some arbitrary initial condition, okay, that well enough satisfies our needs for differentiability, okay? And the way that we're going to approach finding solutions is that we're going to look for solutions along some curves, okay? X is equal to some function of t, okay? So that u is going to be equal to u of x, some function of t, okay? So what does this kind of change of variables do? Well, if we can compute what's called now the total derivative of u with respect to this new t here, then we have that when I differentiate this function u with respect to t, I'm still going to get that partial derivative with respect to t, okay? But I'm also now going to get the partial derivative with respect to x, and then applying chain rule, I'm going to have this factor of dx dt out in front, okay? Because of x of t now being a function in this place of the x argument, okay? So the question is, how do we choose x of t to help us? It looks like this is just going to make the derivatives in our equation more complicated. How can we choose it so that maybe things cancel out so that we get an ODE that we could potentially solve, okay? So the idea is that if we want this is called our total derivative, to sort of simplify nicely, okay? We would like to choose dx dt, okay? So that this total derivative, okay, maybe looks like the left-hand side of this equation, okay? So that I know that as long as I'm looking along characteristics, okay, I can reduce my equation to just the some total derivative of u is equal to 0. Okay? So in order to choose that, then I should choose dx dt equals c of u. Okay? If dx dt is equal to c of u, then when I take the total derivative of my solution, okay, I'll get the left-hand side of this equation, and then I can just say I need that total derivative to be equal to 0, and I've reduced my problem down to just a one-dimensional problem. I just need the total derivative of this function here to be equal to 0. Okay?
Professor,
Yes.
sorry, I got a little confused. In this course, it's always the case that in a partial differential equation, the main variable says u is always a function of your independent variable and a dependent variable, right? We don't have two independent variables, right? Like we would never encounter x and t being independent of each other.
Now, x and t are both independent variables in this case, but we're saying I'm going to change variables now so that I'm only looking at values of x that correspond to a particular value of t. So I'm collapsing the xy plane to a single variable by saying each value of t has a corresponding value of x that I'm going to look along. Okay.
Okay, but truly they are both independent variables.
Truly, they're both independent variables.
Okay.
Okay. But I'm going to say that the way I'm going to construct my solution is I'm going to look along these lines, okay, x of t, where each value of x is associated with a particular value of t. Okay. So it is a way of reducing down to a single independent variable, but the original PDE had two independent variables. Okay. All right. So if I can do this, then this is going to imply that du dt is equal to the partial with just respect to the t argument plus du dx, and now my dx dt is going to be equal to the c of u, and I know that this is equal to 0. Okay, so this is equal to 0 now along dx dt. Okay, and so essentially I've collapsed the PDE to an ODE in this case. Okay, so this helps because, for one, it's going to imply that u of xt t is equal to a constant, right? Because the ODE du dt equals 0, the solution of that is a constant, and it's just going to be given by its initial condition. So this is going to be constant basically along dx dt, okay? And what is dx dt equal to? Well, it's equal to c of u. But now what is u? U is going to be our u of xt t, okay? Or if I like, I can say, well, I know what u of xt t is, okay? It's equal to this constant, just u0, okay? So now I have two ODEs that are involved, right? I have the ODE for u, and I have the ODE for x, okay? So I've taken my PDE and I've turned it into two ODEs that I can hopefully solve, okay? Well, how do I solve this? It's actually not too hard because, again, this is this ODE here, right? it's just dx dt is equal to some constant, okay? So that means that x of t is equal to c of u0 t plus x0, okay? For some x0 that's a scalar that lives in R, okay? So in fact, these are our characteristics, okay? These should look reminiscent of the kinds of things that we were seeing in the case of the transport equation. If I just took, C to just be a straight up constant, this would look exactly like what I got from the transport equation, okay? Now, there's still a couple of things that are floating about that we haven't really defined, okay? How to choose x0 and u0. They just seem to sort of be free constants at this point. Well, first of all, we know that at t equals 0, okay, x is equal to x0, okay? So we have a mapping basically between x and x0, okay? And also, we can then write that in general, right, at any t, we have that x0 is equal to x minus c, sorry about that, x minus c u0 of t, okay? All I did is I rearranged our equation for the characteristic, okay? And in addition, u of x0 this is at t equals 0, is equal to u0, okay? But I know what u of x0 is. It should be equal to f of x0, right? This is just using my initial condition of my original PDE, okay? So I know what x0 is everywhere, okay? I know what u of x0, 0 is, okay? So then I can plug in u of xt is equal to u0, right, is equal to f of x0, okay? And I can replace f of x0, right, with this definition of x0 here. So I get f of x minus c of u, but u0 is just u, so I just have c of u times t, okay? So this is now looking like that implicit solution that I had before, right? U is equal to f of x minus c of u t. Does this agree with things that we've already derived before? Well, yes. If it's just the linear transport equation, then this would just be a c, and I would have f of x minus ct. If this was the Burger's equation, then this c of u would be u, and I would have u equals f of x minus ut, okay? So it agrees with those previous examples that we've worked on before, and in general, it works for any, nice enough function c of u in this case, okay? So in general, I'll just write this over here. If c of u is just equal to c bar, right, some constant, okay, then u of xt is equal to f of x minus c bar t, okay? And this is just linear transport, okay? And if c of u equals u, okay, this is just inviscid Burgers, okay? Then we have that u of xt is equal to f of x minus ut, okay? But it works for anything you like in this case, okay? So that's for sort of general transport equations, okay? We're next going to go to the general method of characteristics, where the bookkeeping gets a little bit more complicated. But first, are there any things I can clarify this or any questions before we move on? Okay. So I just want to emphasize there's a few main ideas here. First of all, you want to take your PDE and turn it into a collection of ODEs. It turns out you're gonna have for each independent variable you'll have an ODE, and then for your dependent variable you'll have an ODE. So typically we're gonna have 3 ODEs. They can be nonlinear. You may have to pull out methods for solving nonlinear systems of ODEs in order to solve these. In this case, it was fairly straightforward. They were just like linear differential equations, okay? And the other thing is that you need to be able to invert these functions, right, that you work out. In this case, they were linear functions, so they were fairly straightforward to invert. It's not always going to be that easy, and sometimes your solution at the end of the